Welcome to another episode of Transparent Physics. In this lesson, we are going to continue our series on dynamics. Specifically, I'm going to show you how to solve another sample problem, this one involving the classic scenario of a sign hanging by two cables.
Okay, we've got a problem dealing with a sign hanging from rest, so let's see what we got and see what we need to do. We have a 9 kilogram sign hangs at rest. The at rest is important, from 2 cables. And one cable pulls up and to the left. Let's note that, but we'll see how that translates in. Oh, there we go, with a force of 23 newtons and an angle of 40 degrees. With respect to the vertical, this is just packed full of information. What is the magnitude and angle of the force in the second cable? So let's make sure we got to remember to solve for both of those. Alright, this is a problem that definitely can benefit from a good sketch, so let's see what we got here. So we have a sign hanging at rest, and really the sign itself is irrelevant. Everything can be represented as a dot. And we have 2 cables. One cable pulls up to the left. The key thing here is it says it's an angle of 40 degrees with respect to the vertical, up to the left. So that's going to make it look something like this. So this angle here is 40 degrees. And then there's a second cable, and we don't know much about that. We don't really know. We don't know the magnitude. We don't know the angle. So I'm just going to call that. I'm just going to call that T and theta. We don't know anything about it. So those are. That's our unknown right now. So we'll give it a little unknown highlight there. All right, that's what we're solving for. And in a lot of cases, and it's 23 newtons. So 23 newtons. Unintentional ellipse. There we are. 23 newtons. And a lot of introductory physics students would sort of stop right there and start solving it out. But just because they don't mention it doesn't mean it's not true. And signs have weight. So we do have a weight that's acting down. It's going to be at 270 degrees. So don't forget to include the weight. And we know that if the mass is 9 kilograms, we know that W equals mg. So that makes the weight of the sign 9 kilograms times 9.80 meters per second squared. So that's going to make the weight of the sign 27 newtons. So do not forget to include the weight of the object, even if the sign doesn't specifically tell you to. Okay, from here, let me show you how you can once again use a vector analysis table to help you solve this out. It's kind of neat the way we can do it. All right, so we got to make room for 3 forces right now. So 1, 2, 3, and double line. Ingredients, recipe for the horizontal direction, recipe for the vertical direction. All right, so we don't know anything about this first guy, so we're just going to write him as T comma theta. We do know something about the second guy. His magnitude is 23 newtons. Now before we go plugging in 40 degrees, let's ask ourselves, is this with respect to the positive x-axis? And I would say no. The 40 degrees is with respect to the positive y-axis, not the positive x. So we have an extra 90 degrees we need to factor in there. So that force, even though it's given to us as 40, should be entered into our vector analysis table as 130 degrees. Every angle that goes in that table must be written with respect to the positive x-axis, or this technique will not work for you. And then finally, 27 newtons at 270 degrees. we get to this point, it's always a good idea to ask yourself the question. The question is whether or not is this object accelerating? And a good sign will not accelerate. I would say that's probably the safe auto minimum for a good sign. So if there is no acceleration, no becomes 0 newtons. So no acceleration in the x, no acceleration in the y. That's going to help us out. So when we go to fill out this table, let's leave the top row blank for a second. The other ones we can fill out kind of quick. This is 23 newtons times the cosine of 130. So when we do that out, we're going to get 14.8 newtons. Oh, excuse me for that one. 14.8 newtons. And the 23 newtons times the sine of 130 is going to equal positive 17.6 newtons. And then 270 is straight down, so there's nothing in the x, and it's all negative y. The sine of 270 is negative 1, so this becomes negative 27 newtons. If you have questions about where some of those numbers in the vector analysis table came from, I do encourage you to watch the Noobster class series on transparent physics on dealing with vectors. We talk about the whole process on how to solve these things out in that series. Now we're left with a bit of a mystery on the top. There's a couple different ways we can tease this out. I'm just going to say, hey, realistically speaking, what should we be getting here? We should be getting the x value. And what should we be getting here? We should be getting the y value. Now we don't know what the x value and the y value are, but I mean that's what we should be getting. So if we take a look at the equations, what we see here is that now we have an equation in the x and an equation in the y, and we can solve for tx and ty. So we don't exactly know the magnitude and we don't exactly know the angle, but in the x direction, we know that tx minus 14.8 newtons equals 0 newtons. So we know that tx has to equal 14.8. And in the y direction, we know that ty plus 17.6 minus 27 has to equal 0. And when you solve that out algebraically, I'm a little tight on space, so I'm just going to tell the answer is positive 9.4 newtons. Okay. And I'll make sure I put a plus there for consistency. All right. From here, we have an x and a y. So realistically, what we've done is we have an x value and a y value. We know that it goes over 14.8. It goes up 9.4. So we are interested in solving for the magnitude and the angle. And again, if this is new to you, I encourage you to go check out the series I did on vector math. That'll show you how to do all this. But in order to solve for the magnitude, t equals the square root of tx squared plus ty squared. So we have our x and our y component. And each of those are squared. And when you do the math, you get 17.5 newtons. And that is the magnitude of that's how much the unknown cable is pulling up with. The direction, we have the inverse tangent of y over x, which is going to be the inverse tangent of 9.4 over 14.8. And when you work that out, you get 32.4 degrees. So there you go. If you want to keep that sine stable, you're going to need to pull up and to the right. The magnitude of the force is going to be 17.5 newtons. and the angle it's going to pull up with is 32.4 degrees. If you want to check if I'm right or not, go ahead, plug it into the table. Instead of t and theta, put in 17.5 and 32.4 degrees and solve it out, and I believe you will find both columns add to 0 still.
Okay, just a closing thought or two here at the end of the lesson. Just remember, even as we dig deeper and deeper into the content of introductory physics, we still often rely heavily on the fundamentals we might have learned in the first couple weeks or months of the course. So for example, in this problem, we're using Newton's second law. We're taking vector angles with respect to the positive x-axis. So one of the challenges of introductory physics is that it often builds on what you learned in the earlier sections. So all that work you put in earlier in the year is starting to pay off now. If you enjoyed using a lot of your old physics to solve new problems, make sure you click the like button. If you have any questions about how I solved that problem out, leave it in the comment section below. And to find out what's coming next from Transparent Physics and to help the channel grow, please click subscribe. Okay, I got to admit, after that problem, I'm looking at that box that talks about the background music by Kevin MacLeod, and I'm just thinking of 2 cables coming off of it holding it at rest. So once you start thinking physics, you see it everywhere. And I hope we made the hanging sign problem a little clearer for you on this episode of Transparent Physics.